In this tutorial we're going to look at some of the more advanced features of network and social graphs and also look at some more complex examples. This tutorial follows on directly from tutorial 3. What we're going to do next is use the advanced mode, so I'm just going to come back to the force graph and we're just going to reset the points. So we go back to our original plot. If we go to the advanced mode, then what we're going to do this time is individually set, if you like, how much spring in it and how much charge we've got. So what we're going to do is start off with a relatively, let's start them fairly equal. Damping and threshold. Damping is basically how quickly it sort of uses up energy. So what we tend to do is actually set that right to the left hand side, which again ironically means it uses up the least energy, so you get the most change as the system runs. Threshold is so we can get it to automatically stop once a certain amount of movement level has been dropped to, but we tend to find it's easier just to control it manually. So if I run this, then again we see immediately everything snaps together. And then if I move charge to the left, we're reducing the impact charge, push charge out to the right, we're increasing it, and I just want to reduce the impact of the spring, and there you see again it just snaps out. So here we are getting the right sense, if you like. So spring to the left means reduce spring, and maximum spreading out, and charge up to the right means maximum charge, so we're pushing the various elements right out. And just zoom back, you see it's spread out over quite a way this time. So hopefully that gives you an understanding of how we use the network function. What we'll do now is just try a different starting layout, because the starting layout can have quite a big impact on how you view the data. So we're going to go back to the nodes and back to the data mapping. What we're going to do this time is, instead of using the random function, we're actually going to deploy the various points into a circle. So what we do is we give it the radius of the circle. We're going to use cosine for this one. The angle we're going to have is actually going to be the ID number divided by the total number of points we have. So we've got a total of 28 points. So that's 1 divided by 28. That'll give us fractions of a circle. So we need to times that up by pi, and we're going to do the same for z, and this time we're going to make that sine, and let's just try that out. And here we are. What we've done is we've told each of the points to be deployed into a circle. And this is a fairly common layout that's used when you're looking at network data. So you can see the points basically where, such as our blue one, which we highlighted earlier on, have obviously got the most lines coming into them. Various points down here you can see have got slightly fewer. But it could be quite hard from this layout to spot the points that have just got 2 or 3 connections, because if they happen to be close to this one in positioning, they get sort of overwritten by all the other links. So it has its uses for particular sorts of data, and as you see we can create it in Datascape just purely by creating a mapping that's based around sine and cosine. We haven't made use yet of any of the other information that we put in the 2 datasets, so let's bring that in. So we're going to go to the node file and go to edit data mappings, and what we're going to do, let's replace colour by city. So there we've got city. Have a look at the sort of range we've got here. We've got 8 different city names in there, so that should map quite nicely to colour. So let's close that and OK. What we now need to do is just create a translation table so as to map the cities onto different colours. Just click on autofill and it randomly chooses a bunch of colours. See if we're happy with all those. Yeah, they look fine for the moment. And click on OK and reload. And there we have each of the spheres coloured in by the city. One thing to note is that whenever we change the mapping, it automatically regenerates the position information, because that's actually part of the mapping, is to run a random position. Hence, if you want to get your colours and things like that, try and get that sorted out sort of initially before you run your force graph, or else you'll have to run the force graph each time you make any change to the mapping. So that will do us for the colour. What we might also want to do though is actually change something like the size and make that dependent on the number of links. We're already using that for the Y offset, but it can be useful to use it a couple of times. So if I haven't defined what I'm going to use, so let's just set that to links. and the range of that is from 2 up to 19. What we might want to do is quite useful sometimes to use something like log. So let's do log of links and say +2, something like that. So that's now going to give us a value between about 2.5 and 5, which is enough in this case to give us a sense of the busier nodes. And let's reload that. And yes, you can quite clearly see which are the larger nodes. And we should find generally it's the larger nodes at the top and the smaller nodes at the bottom. And yeah, that appears to be borne out by the data. If we go back to the links network, the links dataset, go to edit data mapping there. You'll remember one of the things that we specified was the type of connectivity between the different people. So again, what we'll do is let's apply that to color. So we're going to replace color with the link type, and the link type itself again has 4 values, so that's fine. We'll run with that. Click on OK, and we just need to set up color mapping. Again, let's just get it to automatically generate that, and OK, and reload the data. And so now we can see that we've got both the color information applying to the lines and to the nodes themselves. So we're going to run the force graph again. We're going to use the simple value, and let's just put it in the middle somewhere and set it running. Again, everything collapses into itself, and then we're going to increase the amount of charge, reduce the amount of spring, and again as we get close to the edge we see it springs out, so it's a bit of a sharp transition there, and in fact actually that looks like it's relatively stable, so let's just stop it. What we'll do just to finish off this tutorial is just to show you 2 or 3 different other types of network graphs, slightly more complex ones than this. This particular dataset is actually about the interactions of proteins within a plant cell. Again, you can see we've got our 2 datasets here, one for nodes and one for edges. Just have a quick look at the mappings on this. Again, random layout, height is based around frequency. Size I'm actually going to change from 2. Because within the dataset we have a value for the age, which is basically how long the protein has been in that particular cell. So what we're going to do is we're just going to do age plus, 1 plus age divided by 5. That gives us a reasonable sort of effect to it. And just reload the data. And here's the data, so we can see that we've got the height or the size variations rather. Again, as before, we've got the vertical offset to show us how much each individual node appears in the network, and with this number of nodes you can see it's very useful to actually sort of see those being pulled out of the mess. But it's still not a particularly readable network. So again, we're going to apply the force graph. I'm just going to choose 1 point to anchor it, and we're going to go down to force graph. And what I'm going to do here is actually put in maximum spring and minimum charge so as to collapse the network initially. Put damping to the maximum, which is effectively minimum damping, and let's just run. So we can see the network itself begins to collapse in on itself. It's actually reached almost a stable position there. But what I want to do now is I want to bring up the charge so as to separate things out a bit. And you can see we can actually sort of balance these as the network evolves. Stop when we feel it's reached an interesting state, and then go and look and see what's going on. So you can see here it's actually worked quite nicely. It's pulled in this network very tightly. This is the largest network in the system. Here's the second sort of largest network in the system. It's pulled out over here. What it's also done is begun to push out to the edge things like little duplets here. So we've got 2 networks, sorry, 2 nodes, another 2 nodes here which aren't connected. An individual network node here, again not connected, another couple of duplets, another couple of duplets here. So it's acted a bit like a filter, pulling out stuff that isn't associated with the network or closely connected to the network, but then actually showing us where we've got clusters of quite closely connected points. For instance, your nice little group here. So hopefully shows you how we can take quite a complex network and we can begin to use the filtering, of the force graph to effectively filter the network out so as to make it something that's a little bit easier to understand. For this final demonstration, we're going to look at the social graph built from the various developers involved in an open source project. This is the initial layout, just in 2 dimensions. Each of the points represents a developer. The points have been sized and also color-coded based on the number of connections from that developer to each of the others. Also, the individual lines have been sized, so the thicker the line, the more communication there is, typically by email or by chat, between the two developers. If we apply the force graph to the 2D representation, then whilst there's some improvement in readability, it's still not significantly easy to understand what's going on. We can see though that the force graph has done its job. The least connected points are represented in dark blue right at the edges, then moving into light blue as we head towards the centre, then into the yellow nodes, then into the orange nodes, before we finally get to the red nodes. The red nodes, obviously with the highest connections, show a bit more distribution because they've got a link into so many other nodes. The blue node that's highlighted there is just the one that was used as the anchor for the force graph. Here we see the same data but now in 3D. We've used the vertical dimension to represent developer frequency again, so the most connected developers are appearing right at the top of the chart and the least connected developers in dark blue right at the bottom of the chart. And now we're going to apply the force graph to the three-dimensional layout, again starting off with sort of mid-values of spring and charge, damping right off to the right hand side, and run it, and as ever the springiness collapses the chart. Then we're going to reduce the spring and increase the charge so as to spread the chart back out. And whilst it's actually running, we can actually fly around. And once we're happy, we can stop the iterations. So now we have our force graph laid out network, and we're beginning to get a little bit more visibility of actually what's going on in terms of being able to clearly define sort of where the main nodes are and what the connectivity is from them, both at this top level and then also if we drop down back to the lower level. One of the nice things with the three-dimensional layout is actually if we want to, we can actually drop ourselves right down to the bottom and we can see what's going on, if you like, underneath the graph. Typically a lot of this information tends to get quite buried if you do this in a two-dimensional plot. When we've got a network like this, one of the things we can do is, having selected a user, we can actually then see what connectivity they've got. So we're just going to select the most popular user here. You notice we've masked the user identity just with a hash. And I just press the plus key on the keyboard, and that then highlights that particular user's network. And I can then actually tag that in the standard way, switch off the rest of the network, so I just see the network for that particular user. One thing to note is that when you press the plus key, you must have your mouse cursor hovering over the sphere you're interested in. It's not enough just to have had it previously selected. Having selected the most popular person in the network and their network, one thing really interesting is actually to do an inverse of the selection. What that does is it chooses all the people who he isn't connecting with directly. So what we're going to do is tag that and change the name. And switch off the rest of the networks. Bring the lines back up. So what we now have is, you'll notice, a far sparser network. Because we've removed all the direct connections from the kingpin, and we've just got the people left at the bottom of the network, if you like, who are sort of talking at a relatively low level to each other. We can see that the lines are a lot thinner. We've got one particular node here that appears to be sort of the best connected of this second tier. So again, in terms of, sort of what we want to look at in the node and what information we want to get out of it, we've now taken what was a very dense node and given us a different bunch or a different group of points to look at with a different set of criteria. So hopefully that's given you a basic understanding of how we use networks into Datascape, how we bring them in, how we can apply the mappings both to the nodes and to the links, and then some of the functions that we can use when we actually analyse them. Thank you for watching, and please have a look at the wiki to find out more information about how to use Datascape, and please also check out the other tutorials. Thank you.